Good morning, everybody. Thank you for being here. For those who don't know me, I'm Panos Panagos, the project leader of the EU Soil Observatory in the European Commission. And together with my colleague Emanuele Lugato, we chair this session on data approaches, quantification, emission removals, baseline, and carbon activities. This is the first part. We'll have a second part in the afternoon after the plenary. So we invite you to follow as well the second part. The first part will be a kind of presentation. So we decided that in this first, in the morning part, we'll have 6 presentations. So I will ask the presenters to be concise in the 10 minutes that they have. And of course, at the end, we'll have some questions. I will allow us one hot question per presenter, and then we'll have many, let's say, questions at the end towards all the presenters. In order not to lose any time, I will start the presentation. I will give the floor to the presenters. So please, Carlos Alberto Torres Guerrero. Carlos, please. Thank you.
Thank you. Can I use the monitor? Thank you. Okay. Can you hear me well, right? Okay, so thank you very much for being here. I'm presenting before to start. I'm Carlos Alberto Torres Guerrero from Beta Technological Center, based on the University of Vic, near Barcelona in Catalonia. So today I will introduce you the carbon farming method platform that was developed in the mark of carbon farming method project that is an Interreg funded project. So let's begin. Okay, as we know, Mediterranean soils have this vast potential for carbon sequestration if we improve the practices properly. So using regenerative agriculture or agroforestry, we can increase the soil organic carbon sequestration, but we need to measure and track it rigorously through the MRV tools. For this reason, we need to adapt these tools for the Mediterranean because there is a fragmented data. The cost of these MRV are high and elevated for the small and medium farms. We have limited tools in the Med region, and CRCF requires these robust MRVs. For this reason, developers lack operational tools for parcel to landscape monitoring. Okay, so let me introduce the project that is aimed to help the farmers to introduce carbon farming as a new business model, trying to get these additional revenues for the farmers, improving regenerative agricultural practices and agroforestry as well. So we developed four-step methodology. At the very beginning, we created a common framework for the Mediterranean activities on carbon farming method. Then we are running pilot farms in Italy and Spain, 3 in Catalonia, and 5 more here in Italy, and validating our approach that is a hybrid approach combining modeling using ROT-C and sampling. In the third step, we are developing this platform, and in the fourth one, we are sharing and replicate all these learned for inspiring new activities or new actions across the region. Okay, so the main outcomes of this project are these 3 ones, but today I just want to tell you about carbon removals calculation platform. So we are developing this platform that is capable to quantify soil carbon removals, support baseline estimations, project-based, aligned with the CRCF methodologies and with any certifications scheme of voluntary carbon markets, and this enabled the access to this market. The architecture of this platform is kind of easy, incorporating 3 modules with let's say, user-friendly workflows, or this always thinking when we develop a platform. So at the beginning, in the project design, if you can click on the icon, please. We have this manager for tracking all our projects, and we can create. In this model, we are using the Verra certification scheme as an example, but we can incorporate any of these. The advantage is that we can work online for tracking all the changes in these PDDs. The second module is the shock prediction model that incorporates the ROTC model modified by Farina et al. If you click, I don't know if you can click on that. Perfect. So this model is modified by the dryland conditions, and we can track all our farms. When I speak in terms of farm, I am speaking about different plots inserted in this project. I don't know what happened with the video. Could you could you play? Okay, so and the advantage is that we can update, or we can put different plots here with different actions. We can draw in the plot, or we can upload the plot using a KML project. We are using an IP for climate data, so it's not necessary to introduce the climate data. This data set is the Terra and Google Earth Engine APIs or data sets. And then we have all the information related to the ROTC model, that we can create the baseline for the calculation of this project, and the project for the next 20 years, and all the inputs that we need to deliver to the model. What is the advantage of this monitoring tool is that we can use the ROTC, the normal one, and the ROTC TN that is modified by dryland conditions. So in this case, we can calibrate our results provided by the API with this with our data provided by the sampling. And the last module is the GHG gases accounting. That is a module based on LCA approach. So we can use all the inputs, outputs regarding our management in the farm, and we can calculate the emissions for the use of the energy consumption or combustible consumption as well. So and the same line, we can develop the baseline and the project model for different years. So we can put all this, let's say, improved management for integrating the in the general results. And finally, we can get all these results in all the farm, and including all the plots. So then we can see what will be the soil the soil organic carbon sequestered on the soil on the top. Then in the middle, we can see the greenhouse gases avoided emission, and the final one is the total net of all of this. We are validating all this data with our pilot farms, and we are seeking new validating or new plots for validating with this data. So what makes this platform unique, that is designed for project developers and farmers? We create this Mediterranean calibrated shock model, and Roberta Farina is part of this project. We can use as a scenario analysis as well, the GHG module accounting, and the parcel tool landscape scale monitoring. So, but we want addressing these key technical challenges that balance this data confidence versus monitoring cost, harmonizing field data and modeling outputs. We want to representing non-permanence risk in Mediterranean soils. This is very, very challenging. And we want to include an uncertainty analysis. So for policy and market integration, and I will pass to the final slide, we want to develop this transparent MRB aligned with carbon farming certifications in the region. We want to support both in setting or offsetting schemes. It's not just related to carbon credits. And this enables blended finance and territorial implementation scalable for carbon farming business models. So in one line, carbon farming met is a Mediterranean adapted CRCF MRB tool for farmers, developers, operators, and territorial projects. So the last two slides is just to invite you for our final conference in Barcelona next 27th to 29th of May in Barcelona, when we will launch this platform. And if you want to discover more about the carbon farming project, so you can go to our webpage, or this is the Zenodo community when you can see all the documents. And thank you, all of you.
Carlos, many thanks. Okay. Any burning question? Can take. Yes, please.
Sorry, I have been late and I didn't hear about what are your bases regarding the baselines.
Yeah. Well, we are using the ROTC model for produce this baseline. In the first step, we are using the model. This is a mechanistic model with the API data provided by the soil data sets, FAO Harmonized 2.0, and climate data for different data sets, Terra and World Climate. But we are developing these baselines, calibrating with sampling procedures, so we can get more stable baselines, but project basis more than
but the farmers that you have selected were already involved in some regenerative project, or
well, I forgot to mention that the project is involved with regenerative agricultural practices, and into these ones the agroforestry as well. So
thanks.
Thank you very much. We proceed with the second presentation from our colleagues in GRC, Simona Bosco. Simona, please.
Good morning, everyone. I'm Simona Bosco from the Joint Research Center, and today I will show you the result of a project that carried out by the JRC and the European Environmental Agency, and colleagues are also in this room, on aligning the mitigation potential of the common agricultural policy with the reported greenhouse gas emission in the greenhouse gas inventory. Just to give a bit of background shortly, as you know, the agricultural greenhouse gas emission declined substantially until 2005, and then more limited reduction. We had a limited reduction, and intervention that are in the current CAP aim at reducing emission and increase the sink. To try to better estimate the mitigation potential of the CAP, a first ex-ante study was carried out by the Evaluation Help Desk together with DG Agri, and to evaluate the mitigation potential of the 27 member states, and the report was published last year. This study was relied on several data sets and tools, and including the classification of farming practices, the labeling of this intervention that are in the strategic plan, and for the first time, this study was done at the farming practice level, also using coefficient from the scientific literature, and in particular also from the JRC Farming Practice Evidence Library. The result of this study estimated a mitigation potential of 35 megatons emission per year and plus 32 megatons per year from protection of existing carbon sink. This mitigation comes 80% from an increase in soil organic carbon from cropland, and it's quite a huge number considering that is more than 70% of the target for LULUCF by 2030, including forestry. On the contrary, there was very little from livestock because there were very few intervention or reducing emission from livestock in the strategic plan. In the report, the author already highlighted the main limitation of this study, that were mainly the uncertainty in the uptake of the intervention by farmers, the additionality over time of these practices, and also the fact that some practices are already implemented in the previous CAP. So this raised this question on why do these evaluation helpers estimate differ from the emissions that are reported in the inventory. And the main reason is that the two systems use different methodological approaches and data. Indeed, while the evaluation helper study is a policy evaluation approach, and it focuses on assessing the climate mitigation potential of expected uptake of CAP-supported farming practices, the greenhouse gas inventory uses an IPCC accounting approach focusing on reporting the estimate every year at national level of emission and removal. And these emissions are calculated using activity data, emission factor, and models that are in line with the IPCC guideline. And they have also a consistent time series since 1919 on the uptake of farming practice. So they are already part of the baseline. This has some key implications. Indeed, main CAP-supported practices may be already included in the greenhouse gas inventory, and the time dynamics that is included in the inventory may limit additional mitigation. Then the data requirement and the methodological rules can also constrain how practices are reflected in the two exercises. So to try to better identify the differences between the two studies, the JRC and the EA launched a project in 2025 on streamlining the greenhouse gas mitigation potential of the CAP with the greenhouse gas inventory. And we did it working with member states on case study. In particular, we worked with Austria and Italy, involving both the CAP team and the greenhouse gas team. And a third case study is ongoing with the Netherlands. The two main objectives of the project were to align the estimate of the evaluation of the study on the CAP with the greenhouse gas inventory, but also to try to assess the extent to which the CAP-supported farming practices are already included in the greenhouse gas inventory. And we did it using a methodology based on three main steps. The first step was trying to match the farming practices that are included in the evaluation of the study with the ones that are included in the greenhouse gas inventory. And this was a key challenge because the two systems talk different languages. Indeed, while the greenhouse gas inventory is organized by emission category, the CAP strategic plan are organized by intervention and different payment type. So the common language can be farming practice in a way that we can link the two systems. To do that, several data were needed. On the greenhouse gas inventory side, we started from the information included in the greenhouse gas inventory report, and particularly on the additional data supporting the inventory. On the CAP side, we were working with the intervention linked to the result indicator linked to the mitigation, climate mitigation, and we also used the labeling of this intervention. We found out in the case of Austria that there is a partial match between the list of farming practices of the two exercises, and the main practices are included in both, but this is also due to the fact that in the Austrian case, the CAP data are already included in the greenhouse gas inventory, in particular in the LULUCF. It was different from Italy, where we found a poor match with only cover crop as the only farming practice present in both exercises. And indeed, in this case, CAP data are not the main source of data for the LULUCF sector, and they rely on more comprehensive data, like, for example, the one from certification bodies, like for organic farming. So the second step was about comparing the methodologies, the activity data, and the assumption in the common farming practices. As you may imagine, the source of data, emission factor, and assumption can affect the estimate. And just to mention the two main aspects, activity data and time dimension. For the activity data, the access to the IACS data is fundamental and was not possible for both member states. And also the time dimension, especially for carbon, is quite relevant, and there was no time dimension in the evaluation help study. Just to illustrate this importance, here on the right, you see the plot on the annual carbon stock changes in cropland in Austria. This is from the Austrian greenhouse gas inventory. And you may see that when they started the farming practice from the CAP in the 90s, they see an increase in the carbon stock. But since this farming practice were there for more than 20 years, slowly, this effect is decreasing, and recently this sector is again source of emission. The third step was the comparison of the 5 years mitigation potential of the CAP period with the greenhouse gas projection, in particular with existing measure scenario that is already including the current policies, already including the CAP. As you may see in the difference for the two member states between the geographic projection and the evaluation at the study is not only the size of the mitigation that is different, that is much higher for the evaluation help the study, but it's also the distribution between agricultural and LULUCF. In the case of the evaluation help the study, most of the mitigation was from increase of carbon in stock of cropland, while in the case of the greenhouse gas projection, it was mainly due to a reduction in emission from livestock. So from this analysis, we identified some key findings. And the first, as already shown, is that the mitigation potential in the evaluation help the study in the greenhouse gas projection is different. It's from LULUCF in the evaluation help the study and from the agricultural sector in the projection. And another important finding is that much of the mitigation potential identified in the evaluation help the study reflect practices that were already implemented in the previous CAP. The third point is that most of the CAP-supported farming practices are already captured by the greenhouse gas inventory. Only some of them, in particular the one related to spatial explicit analysis, are not yet included, like, for example, landscape feature. CAP data are already partially included in the greenhouse gas inventory, but due to the nature of the inventory that has to capture the entire agricultural system, multiple data sources are needed to improve the sector. And another point that we discovered is also that it's not possible to disaggregate the effect of a single farming practice in the greenhouse gas inventory, both because in the inventory we have more management practices and also for the calculation of this estimate. Based on this finding, we identify some key recommendations to improve the alignment between the CAP and the greenhouse gas inventory. First, a common language is needed, and indeed the use of an harmonized classification of farming practices in the next CAP to describe the CAP intervention would help a lot. Then it's also important to systematically track the uptake of CAP practices in a way to build a time series on uptake of these practices. The third point is more on the inventory side. It's fundamental to ensure the availability of parcel-level IACS data to the greenhouse gas inventory compilers to improve the LULUCF sector estimate. And the last part is more on improving the greenhouse gas inventory to improve the coherence between the sector for farming practice that affect both carbon and nitrogen cycle. With that, I conclude. Thank you for attention.
Thanks, Simona. Many thanks. Really excellent. Thank you. Any burning question from the audience? I don't see any. Okay, thank you again. I pass the floor to the third presentation. I'm calling Michele Croci. Present an hybrid aligned MRV system with again air observation proximal sensing. Michele, please. You have 10 minutes.
Yes. Okay. Okay. Hi, everyone. Okay. Can you hear me? Okay. My name is Michele Croci, and I'm a researcher at Catholic University. The work that I will present today is the output, or some preliminary output from several projects. The main project is Agritech, the PNRR project on agriculture that found my position, research position. The Marvic project and EO Agri-Twin project that is a tender project with the idea to develop a digital twin for the agriculture. Okay, our approach in general is to develop a hybrid approach to avoid the problem of both measure and remeasure approach and pure model approach. The idea from our work is to, it's not so original maybe, yes, but to merge all the information that can be collected with the remote sensing information and feed this information to improve the and speed up the input that we need to run the model. That can be the model of crop model, or soil biogeochemical model. We think also that the baseline must be configurable, and we need for different step of the development of a project develop a different level of complexity of the baseline, from a fast screening for a rough overview of the supply chain and the landscape until the field parcel level information. What we are working on can be split in three main pillars. The first pillar is on soil mapping and soil monitoring, where we are working on developing a machine learning model to estimate the soil organic carbon concentration. And we are working, but I will not present nothing about that, the use of proximal sensing to map in a fast way the variability of the soil and quantify the soil organic carbon and the property of the soil. Another important step where the remote sensing can be very useful is to map the variability using, for example, the synthetic bare soil index to guide the sampling position and improve the cost efficiency. The second module, the second pillar, is the crop mapping and the crop monitoring, where our idea is to develop a crop model, early crop mapping algorithm to estimate, to classify the different crops during the season. And during the season, the second module of the crop mapping and monitoring pillar is the phenology estimation with different approach. And after, with the information of crop map type and the information of the phenology, we can feed the a simple light use efficiency model to estimate the biomass and the yield. Regarding the proxy verification, we collaborate with CNR in the developing of a crop cover detection algorithm from multi-temporal indices, and we work on tillage intensity and crop residues monitoring. More deeper in the approach. For example, we use the combination of harmonized Sentinel Landsat dataset to have a better synthetic bare soil index, and we combine this the synthetic bare soil index with the terrain attribute and a regional database from Emilia-Romagna region. We compare several algorithms, and between this algorithm, we use also the foundational model, and this model outperformed the classical machine learning model. Regarding the smart soil sampling, It will be on a presentation on that in the tomorrow. We are working on a combination of synthetic based soil index and the inverse of synthetic based soil index, that is just the vegetation. We calculate the quantile information about static information that can be used to run the different algorithm. And in this case, we identify that on 700 sampling, to reach a high accuracy of in terms of GSD, we need just to reach the elbow, we can collect just the 15% of the sample. In combination, this smart soil sampling methods can be used to several methods can be weighted in terms of accuracy, uncertainty, and cost to identify this the right method regarding considering the cost that we can assume and so on. Regarding the crop mapping type, we are working on the combination of Sentinel-1 and Sentinel-2 to monitor from March to September the crop type. We started from our province, but the idea is to upscale to the Po Valley, and we reach a high accuracy for 12 crop class. We consider also, considering the crop type, we consider also the uncertainty using the Shannon entropy yes. We no. There's sì, bueno. Puoi andare indietro, 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 indietro. Okay. Regarding the crop, so okay, thank you. Regarding the crop phenology, we try to do an ensemble of several methods for the estimation of start and end on the season. And for a specific crop, we reach a high accuracy, and this is tomato, and we reach approximately 10 days of root mean square error. You can go. Puoi andare avanti. The information about start and end of the season and the crop type information are used to feed the light use efficiency model. And we apply all this information for a specific province, and we evaluate using the ESTAT information. And also here we reach a good accuracy in terms of RMSE and normalized root mean square error. Avanti. This is a map of combining the crop type. This is tomato, the information of start and of the season, and the information of crop yield generated. Avanti. In summary, the idea is to, okay, grazie. The idea is to fit the ROTC model with crop map, crop rotation map, phenology information, and biomass information, and soil property information, and in the future practice verification to fit the ROTC model to create a specific baseline. In conclusion, yeah, this is an approach that we apply for our region, for our territory, but maybe for a different territory is a better another approach in considering different amount of data available. And we think also that the platform for carbon farming need multi-level tool, and the approach must be multi-layer and multi-level.
Many thanks, Michele. Any burning question?
Yes. Because it's simple. And need very few information to run a simulation. And it's fast. We run some simulation for a specific case. It will be in a presentation in a next session. Marta Bertola, yeah. Maybe.
Some questions for the end. So we'll give the floor to the next presentation, Alessia Castellucci. Alessia, please.
Castellucci, la prima. Okay. Hi everyone, I'm Alessia Castellucci. I work at a company called Horta within the BASF network, and we are a digital company providing agronomic services to farmers and food value chain. And I'm here today to present a system to harmonize all of the data that is required to represent complex systems within the food supply chain and the fields, agronomic fields, and how to present soil health and climate adaptation. And yeah, so the services that we provide are based around decision supporting systems, and we have different tools integrated within the same system. And so we have specific agronomic DSSs that how does they work? Basically, very quickly, they collect data from different sources that can be sensors or standard databases, or also farmers, and also remote sensing. And the DSSs interprets the data and elaborates them using mathematical equations and models. Sorry, and then give back an output that is quite easy information and useful for the farmers that have to decide how to manage the crops. And yeah, so within the system, the data required is quite varied within topics, and because they span from plant disease and insects to weather and soil. So it is quite a holistic system. And we have also a sustainability part that is called Use Sustain tool. And we have greenhouse gas emissions reported and assessed. And then there is also soil organic carbon accounted into a process-based model. And these indications, this information about sustainability is then reported to give back an easy for the food supply chain. And all of these process can be verified also from third parties and using remote sensing and other methods. Okay. Looking, having a deeper look at how the uSustain tool works, we basically have different databases that are created from different sources. And we can, as I said, we can go from weather trends to soil analysis and emission factors to calculate indicators. The important part is also that the farmer inputs some data that is specifically about field operations, and they input the field operations after that they receive the output from the DSS. So they give the advice and then decide, they see the advice and then they decide what to do and input inside of the model and record the operation. Then there is a water balance integrated into the system that is also crop specific and gives daily soil water content. This daily soil water content it comes from directly weather stations and direct measurement. And this soil water content is one of the factors that are involved into the decaying of the organic matter of the soil organic carbon model. The factors are also soil temperature, soil coverage, and soil tillage, and also soil organic carbon or organic matter inputs to the soil are very important factors for the model, for the degradation of the organic matter. And the output of the soil organic carbon model is daily soil organic carbon and CO2 emissions. So, as I said, databases are the core of the system, and they cover for the estimation of different factors and within the tools. So it can cover the soil features, weather, or also the biomass estimation, and that is required for the estimation of the carbon inputs to the soil. And also fuel consumption is estimated for the usage of tractors. And so also soil cover and the organic matter and nitrogen and all of the nutrient input from the fertilizer, and also the impact that come from every product, and also the plant protection product. So are quite varied also for the sources of the data. That can be also soil map, international soil maps, or international databases like emission factors. And we have different sensors connected, like weather stations and soil sensors, and also remote sensing and satellite images. We use also field trials to provide specific information that is needed for the crop models. And a key factor is also the expertise of scientists and expert people, because it is also required an interpretation of the data that is required to harmonize the different sources in different regions also of the world and Europe, and different topics. The data that the users need to upload into the system are quite basic for the food value chain, technicians or farmers. So we have a basic plot description, and then soil features, the cropping system layout, that can be the spanning of how the rows of the crops are set up, and then information about groundwater for the soil water balance and the irrigation information, and then also the cropping management that is involved in almost every output, almost every estimation involved in the DSS system. Okay, we use a soil organic carbon model that is a process-based model. We call it RSC, and it is including the factors that I said before. It involves the estimation of soil carbon for the first 30 centimeters of depth in the soil, and it is calibrated for the more arid systems that come from a more than 4 years data set collected from greenhouse gas emissions that were recorded in 2 sites in Italy. And then how do we use this data? We use basically soil organic carbon from the model to estimate soil organic carbon sequestration. And then greenhouse gas emission reductions are accounted from the indicators. And we use a baseline that can vary according to the standards that are used. And we are connected, like we approach the Verra standard, but we can also make estimation of the baseline waiting for the CRCF finalization. And there is more to just carbon into the energy sustain tool, because every indicator applies the LCA approach, and so it gives information using this quite easy to understand radar chart that is an aggregation of different indicators within 6 compartments. And every indicator is, not every, but we have certificated indicators for PEF, APD, and also ISO 14000. And we have information about biodiversity and soil health. This can be verified, I'll do very quickly, using satellite images and indicators like LAI and uploading documents. And so the MRV includes both soil organic carbon and greenhouse gas emissions, and it is adaptable to different standards. We have a broader sustainability that is the key to have real results, and we are approaching the Verra standard, and as I said, and we a nitrogen module to the soil organic matter model is under development. Okay.
Many thanks, Alessia. Any burning question? If not, I pass the floor to Timo Brer from GRC, my colleague, who will give a flavor of the work that we do there. Thank you.
Okay, so hello everyone. I'm Timo Brer from the Joint Research Center, and I'm presenting here today the work on the EU-wide ensemble approach for the standardized baseline, on which I work together with these colleagues. No, it's not going. Any problem? Oh, okay. Thank you. So the next one, please. Okay, so very short on the definition. So the standardized baseline is essentially where a carbon farming project is compared against the emissions or the carbon removals under similar conditions inside the area. And yeah, in theory, the standardized baseline has a benefit in that it can balance under and over crediting under the assumption that it's unbiased. So we at the GRC had the task to come up with a methodology. So there are many, okay, and that was the following. So we had two different methods, a statistical model based on the Lucas EU-wide soil survey, and constructing a descent, perfect, thank you. And constructing a meta model based on the available EU-wide simulations from the descent model. Then these two approaches we compare to regional methodologies from the mission soil projects. Okay, so essentially the first approach based on the Lucas survey is an elaboration of a model that was created by our former colleague De Rosa et al., where we implemented the simplification of the land cover classes included in the model to account for newly available Copernicus layers published by the EEA. And this also allowed for a simpler classes, but also for including a few more orchards and cover crops. And then we implemented some other changes where we included pH and autocorrelation in the residual structure. So here you see a quick schematic of this approach. So on the top, we implement the model based on the Lucas data. And then, we apply it for a region using these management layers from the Copernicus that I mentioned before. And that was work done by Fernando Fao et al., currently under review. And here you see an example for a region where you have the 10-meter resolution crop map for permanent crop or arable land, lake cropping systems, and also land use change. Then the second approach is building a meta model based on the descent simulations. And essentially this allows us to account for management information as well, and also upscaling based on satellite-derived information from MODIS net primary productivity. So briefly, we take the time series data for the 91-23 period, and we extract it for a 9-kilometer raster across the EU, and take the annual time series for 1999 to 2008. Then we sample systematically from that data set, and we actually extract the subsequent time series for the 2009-28 period that overlaps with the Lucas survey. And we use this data set to test the forecasting capacity of our model. Then we built the model using basically the input data from descent, which you can see listed here. And we tested two different approaches. So the quantile random forest and the recurrent neural network, where the difference is that the recurrent neural network takes the time series as an input, whereas the quantile random forest we derived from mean statistics for the time series variables. Then we apply both of these models on the 2009-2018 data set that overlaps with the Lucas survey to test the forecasting capacity. So here you see some results. On the top line, there's the training data, where actually both models perform more or less equally, where the random forest actually outperforms the RNN. But then once you go to the forecasting capacity, you see that actually the accounting for this dynamic component for the whole time series approach with the RNN increases the forecasting capacity. So we proceeded with the RNN for that reason, and we also did a sensitivity analysis where we built different models using various input scenarios for net primary productivity, but also the carbon inputs directly. And we see that it actually performs in line with first order kinetics, but that this sensitivity is slightly weaker when we use entropy as input, of course, because of the indirect relation compared to the carbon inputs themselves. Then, as I mentioned, we applied these two methods to regional case study areas that were also included in various mission soil projects, and they spread the range across the EU. So we cover a variety of better climatic conditions. Here there is a part of some of the results where you see the the carbon changes over the 2009 to the 2018 period for the various models. And you see that the green box plots and the red ones are slightly different, where there's the original descent simulations and those where we use the MODIS MPP and the Copernicus layers. And these can be explained by the difference in the MPP and the land use layers. So that is good. So you can see that the NPP is consistently lower than the MPP generated by the submodel and the descent simulations. So you would expect to have a lower delta SOx in general because there's less carbon going into the system, so you would expect more losses. However, if you then compare the Korean land cover, which is used for the descent simulations, to the one from the Copernicus, you see that actually grassland is actually increased at the cost of arable land and lay cropping. So that's why it compensates for this lower MPP. And the MPP over the carbon input ratio, we also used it to harmonize with the data that we got from the mission soil projects. So essentially, we took the NPP over the carbon input ratio from the simulations and corrected the carbon input data that we have from the mission soil projects, where you can see here in the top box plots where you have the MODIS, the descent, and those corrected from the region. So it's more comparable to how we built the model. And overall, we actually saw that by changing the carbon inputs and correcting it with this method, we approximated better the regional estimates of the baseline. So that also illustrates how not only different models are important in an ensemble, but also the different carbon input scenarios. And then lastly, about the similar circumstances, so Article 4.8 in the CRCF. It's a long definition, and we sought to work on providing a solution to this. So essentially, we took all the input data for the two different approaches, excluding the management variables, and then we applied this on the NOTS administrative level. So these is also where the CAP payments are distributed, so you can assume that socioeconomic and technological circumstances are comparable. And then we perform a multivariate outlier detection on all the input data for the models, and we come up with a selection of sites that should be included to make a standardized baseline. And here you see this for two different areas. There's a few things that we see. So the carbon project is represented by the fields here, whereas those selected based on the multivariate outlier is the cluster, the orange box plot. So there is difference between the modeling approaches, of course, but the ensemble had some mitigating effect on this. And then another takeaway is also that actually large relative differences between the fields in the cluster can be quite small in absolute terms. So then, as a conclusion, so the methodologies are presented, they can account for management information, organic and mineral and fertilizer, irrigation and cover cropping. And this can be applied on a regional scale anywhere in the EU. So it's highly scalable. Then we saw that there's a need to implement time series data so you can account for what's actually happening in the fields, as we saw with the difference between the MODIS MPP input and that from the descent. Of course, this can be improved once you have parcel level agricultural management data as well, for example, from the LPIS. Then the ensemble can provide a conservative estimate based on different methodologies. But it's also important not to think only about different modeling approaches, but also carbon input scenarios for the same model. And that was really briefly it. So
Okay,
thank you.
thank you. Thank you, Timo. Excellent. Please.
Two questions. First one is what target depth are you looking at? I know Lucas' data is mostly 0 to 20 centimeters. When you do that set for the model, I was wondering if you correct, that's become 0 to 30, which allows me what the math is already. Then the second question is, how do you plan to work it forward to 5 for setting off it?
Okay, thank you. Yeah, so regarding the first question, indeed, it's a 0 to 20 depth, the Lucas survey, and therefore also all the derived modeling exercises from it. But indeed, we corrected by this, let's say, in a relatively simple approach for a depth distribution factor of organic carbon based on different land use classes. Yeah, so then naturally tilling kind of homogenizes the topsoil, whereas grassland you would have a different distribution. Yeah, and these were taken from the literature. So yeah. And this
Question? Yeah.
Well, I mean, so this was basically, yeah, we were contracted by DG Klima to come up with a methodology. Yeah, the idea is to create a platform where different models are available, and it can provide a benchmarking exercise, let's say. That would be, because of course there's a lot of limitations of these scalable yeah, approaches. But the idea would be that there are different yeah, models included in the ensemble. Thank you.
Move towards the last one. So I'm calling Angela Righi. Angela, please, for the last presentation, then we'll have a kind of discussion, please.
Okay. Good morning, everyone. I'm following my colleagues and still talk about ROTC modeling in this presentation. And our goal was to establish a carbon storage, the maximum carbon storage capacity in Mediterranean soil, in arable Mediterranean soils. And why it's important to know the maximum storage capacity, because every policy that we can implement and every payment that can be done needs a change in the production system from the farmer. And we thought that the farmer has the right to know how much room he has to increase its carbon content, because the rate of accrual is actually a logistic curve. So if a farmer knows that it's very far from the storage capacity, it might be stimulated to go through any carbon farming practices. And another factor that it's very important for the model we designed is that carbon storage is strongly influenced by pedoclimatic condition, and we didn't want to look at any management or past management condition, because we wanted a baseline that could be like the purest sort of. So yes, the aim was to produce some pedoclimatic maps for the maximum sock stock estimation. Our data set were from the Lucas campaign, the 3 Lucas campaign 09, 15, and 18. And we also managed to have access to the Western Balkan data from 2015. For the climate, we use the Lucas dataset, the CRU time series. For primary production, the MODIS Terra. And for bulk density, since some points in the Lucas dataset are not do not have the bulk density record, we use the European Soil Data Center TIFS that has a 100-meter resolution for both 0 to 10 and 10 to 20 centimeter bulk density. Lastly, the ROTC has been implemented in R. We tested 3 different methodologies, and to give a robustness of the final result. And the common assumption between these three methodologies is that we wanted to refer to the maximum capacity as if that soil was a permanent grassland. So we kind of modeled arable soil in a permanent grassland. So first of all, the first method was inspired by the work of Pacini in 2023, and it's a probabilistic clustering method that divides the Lucas soil points in pedoclimatic clusters, and these are the final variables that have been used. And since we wanted to, this work has been done previously, but we wanted to harmonize it with the Balkan dataset that actually has the texture variables as categorical. So we kind of transformed every numerical variable into an ordinal one with a scale following the gradient from less clayey to the most clayey. The second method was an extreme gradient boosting. Actually, we tried a different machine learning method, and this one was the one that performed best for us. And we predicted every arable point as with the model trained on the permanent grassland. And lastly, we implemented a T modeling that as it has already been said, has 5 carbon pools, and it's pretty simple compared to other models. So we kind of have the majority of variables available for all the Mediterranean points we used. And since for permanent grassland, the productivity data set are not available, inspired by the work of Zhang in 2026, we modeled the carbon input efficiency from the net primary production with a Markov chain Monte Carlo that estimates the coefficient that for the carbon input by an iteration of 5,000 times. And we did this on all grassland points. So this is the result of the first pedoclimatic clustering, and I gave the restraint of having at least 3 permanent grassland per cluster. And for every cluster, the median value of permanent grassland has been compared to the soil organic stock of arable land, and this is the difference. And so we kind of think that taking the median value for permanent grassland could be a potential goal for all the points in the same map. This is the result for the gradient boosting, and this has been modeled on the crops, orchards, and the temporary grassland. And this one is the delta in soil organic carbon stock. I wanted to show this because I got pretty upset when I saw that there were some points that actually lost soil organic carbon stock, and the answer I gave to myself is that the majority of places where we see the loss are actually places where there is a lack of permanent grassland data. So maybe it's worth considering that this is a methodology that can work for more dense permanent grassland data areas. And lastly, the result for the modeling. I'm showing here the testing points for the permanent grassland that have been validated for 2015 and 2018. And the other map shows the soil organic stock changes between the first and and the 2018 campaign. And going to the previous slide, we see that there are some grassland that, not some, almost half of them, that loses between 2009 and 2018. So maybe that's why we kind of have to face that even taking into consideration strong landscape, such as permanent grassland, the last decades of data already go, I would say, through a loss due to climate change. I don't know, maybe it's also management system that changes. This is something that we, from the Lucas campaign, we don't know, but that might be an answer for why some points go with a loss in the future. And finally, the pedoclimatic cluster has been repeated, but only in Spain and in Italy, because these were the only places where the permanent grassland points were. And 9 clusters were identified. The values for the coefficient obtained before with the Rotsi model on permanent grassland have been used as the coefficient for all the arable points, and the graph shows the plateau reached at in 100 years for all the clusters. So this is actually a percentage, okay? And yeah, that's my the final result. You can see is more or less consistent through grassland with the 3 methods, and these are my take-home points.
Invited the speakers to come from. Yeah, that's a good. Yeah, that's one. Yeah. If we have curiosity about the method that you apply, why did you not consider the cluster in the back of carbon map really relevant by the maximum cluster? And especially to identify the historical depth of carbon input, how did you initialize the cluster? Is that different, or you apply any without enough?
Okay. So for the first question, I think that it can be actually something interesting to implement in the future, because this was like a preliminary work. And for the second question, we initialized with some pedotransfer functions where from the initial point, it was not supposed to be at equilibrium.
Okay. So we now open the discussion, and we have short times for discussing. But I remember there would be the session in the afternoon, just the same title. And yeah, we saw in this session the different methodologies, different approaches, harmonization methods, benchmarking. But if you look at the title of this presentation, there was a keyword, consistent. And what I would like to discuss with you is if now we apply the same carbon farming practices in the same farm, are we able to produce, to quantify the same amount of units? Because this is something that the market wants now. To have a credible market, should be as much as possible independent from the method. So what I would like to discuss with you, are we ready to do that, or we are far away? And how can we improve, or we can give up and say, okay, it's not possible, we put everything done. So we just put some, okay, that's right. Yeah. So there is here some question, but I would like to to open the floor, and I don't know if panelists has already an idea, but it's open, of course, to all the audience. So, yeah. So, the question are how we can apply methods that produce consistent for results. There are some key points. We have to benchmark better the modeling. We have to do calibration procedure. We have to work on the data set harmonization, harmonization of satellite product. So we have to ingest farmer data, and I would like that open the discussion and see if any of the panels can say something or so please, who wants to start? I see some people. Okay.
Yes, hello. Mark Stepp from Switzerland. A question to all of you. So we are talking about strict or robust methods. Does anybody consider like density and its dynamics over time for the calculation steps?
Yes. Yeah. Okay. In a carbon farming met platform, we have the capacity to create this ROTC model running, let's say, in the normal way, but in the latest version that was modified by Farina, we can use bulk density and silt content adapted to the Mediterranean conditions. So no. Yeah, sorry. Now we are using this bulk density, trying to develop better estimations for carbon accounting in the ROTC modeling. Good question. Yeah.
Thank you. I think we have to be sure about 2 points, and at least in this round, we should not forget that. When we calibrate ROTC models with real-life data from the soil, it comes with a high level of uncertainty. When we apply optimal sensing, it comes actually with even more uncertainty than signal. For me, the results are not very convincing. It's very hard to abate that, because that's up to a certain degree this high complexity, but that's a fact. So due to the high level of uncertainty, we probably will not see significant changes of carbon stocks just by changing crop rotation, for instance, or cover crops. So we will see methods like biochar application. We will see application of composts, maybe with impurities of plastics. These materials have never been applied in Rothamsted. So we use models that we cannot predict easily, and we apply methods that the models have never seen. And I'm fully aware that it's very hard to overcome these challenges, but I think we have to be aware. I don't want to wipe away these challenges because it's cheap, easy, and fast, because the clients who buy these credits, they will take these numbers for given. They will not counter-check them.
Thank you. Yeah, just to note that the biochar is not part of the carbon farming. Yeah? It's out, so it's accounting another certification. Yeah.
Just formulate this, Matthias Kunert from University of Aberdeen, just formulate this as a question. For me, the question is, yes, we saw also in the different presentations the different complexity of models used. As was mentioned, ROTC is mainly used because it's easy to apply. A lot of companies use this as an option to do. So considering the consistency that was asked here, we need to have a protocol, and we see how these models are applied. There's different knowledge about using these models, experience, how to set it up. It was mentioned the uncertainty, which you can address, which is also introduced by using different tools. So what would be the way forward? Should we agree to the simple solution, accepting the uncertainty, or should we push the standards high to machine learning, to nascent applications, to other things, which will reject a couple of people joining these concepts? So what would be the solution forward? Should we have high standards or keep it low and just agreeing on ROTC? What do you think? Would you be able to improve using more complex models to improve the results and reduce the uncertainty?
Thank you. Okay, so agronomic systems are very complex, as you said. And I don't think that now we are ready to have a standardized way to get some standard results, because different practices get different results in different cases. So the models are a help to represent what is happening in the real fields, but we need we still need some human experts to put down a good strategy case by case. And I think that we can do some more work on this. And yeah, there is some potentiality, and yeah, like studying effects of different practices is always a good thing. And yeah, so
yeah, thank you for the question. Yeah, I think yeah, in the end, there's also the tension there between making it would be a different answer, I think, based if you're looking at the standardized baseline or project specific, because in the end, if you can constrain your model sufficiently with the data that you have available, then you can maybe move towards other approaches that are less simplified, let's say. But yeah, there I think also, in my opinion, the harmonization in the use of the data is super important also for that reason, especially if you start comparing different modeling approaches, because already using a different type of land clover classification on a regional level can lead to substantial differences.
Pierre Fede-Claude, Polyarsa, small company based in France. I don't want to be the devil's advocate here, but the bottom line is that the accrual rate of soil carbon due to land use changes or cropping practice modification is about 100 to 200 kilograms of organic carbon per year. And what I'm seeing here is the error rate can be like tenfold, 3 to 10 times that amount. If the ultimate idea here is to quantify carbon credits that can be sold and bought on some market, voluntary or not, I feel that we're way off the target. And my question is soil modeling, soil sampling, and all this modeling effort, hybrid or not, the real way to go? And if I was to buy one of these carbon credits measured as such, I would. I don't see how they can be. And this is the point of MRV and all this carbon summit in a sense. And I don't know if we're on the right track, but.
Any reaction? Even from the audience, huh? Even from the audience, if you want to react. Yeah.
Well, I think that there is some work to do, standardized data sets to have standard baselines are one of the main objective that we want to have a standard, also a standard estimation of carbon credits. And soil organic carbon varies a lot through the years, through the seasonality, and there is a lot of factors involved. And so this is why we have to to create protocols and not that like there are already protocols explained and like very used, and but what we don't have is like a data set of baseline for the baseline to use in every case a good baseline and always the same type of estimation.
If I may react now, and if you work at the continental scale now, I work a lot on modeling a continental scale. Of course, you get a prediction of 0.6 now, and the uncertainty is very high sometimes. But if you work on a very more local scale, and you are able to calibrate the models, I think the uncertainty is reduced. So I think that if you have data, good data, and even that if models are not perfect, of course, because we know all the limitations, working that at a more or less scale with good data, you are able to constrain and reduce the uncertainty. I think it could be, if you want, acceptable for the carbon market. That's also other aspect, especially to monitoring the activity in time. So there will be other mechanisms to monitoring the activity in times as the practices that we know as some, let's say, benefit also for outside the carbon. So it can go. So that's of course a compromise. Otherwise, we never end up now if you want to have an uncertainty almost to zero. Yeah. Yeah. Yeah, but did you want to see? Yeah, yeah. Oh, okay.
Yeah, no, definitely a great point. Uncertainty is high. I think we always have to balance economic viability for projects with scientific integrity. And in the case of standards, we did a lot of work with Vera. They have to make that work in a way that projects have a business case, and still that on the portfolio level of the registry, there's no overcrediting happening. And to do that, they basically set the confidence interval lower than what scientists would normally do. In Vera, for example, it's 66%, which seems low on a project level, but it does make projects economically viable. And on the portfolio level, which Vera is looking at, of like hundreds of projects, there's still the probability of overcrediting on a project level is still extremely low. And without that adjustment of the confidence interval, I think with modeling, it's currently not really feasible to make it economically viable. Obviously, for the design-based estimates, measure and remeasure, when you look at sampling there, if you look at large-scale projects, it actually works out fine again, because the variability of soil organic carbon doesn't linearly scale with size. You might have a project area that has 500,000 hectares that has the same variance than a project area of 5,000 hectares. So you need basically to achieve the same precision, you need the same amount of samples. So scale really matters. And with scale, you can make it financially work as well in the case of the carbon market.
Yes, thank you very much. I'm Wiebke from Regeneration, one of those Vera project developers. Thank you for presenting all the models. My question would be, what role do you see for the soil samples in the actual implementation of the models? Like, when do you do it, and how do you use the soil samples over time? How are your models improving with the soil samples? Yeah.
I think that soil samples are essential for initialize the model, and for sure also for the verification. And for example, in the presentation that we have tomorrow, we will speak about that on how guide the sampling using remote sensing to improve the cost accuracy. For sure, there is the trade-off of cost accuracy that is the main problem of the measure and the remeasure.
Very brief. I think, yeah, the sampling is a key point about all these models and how we can calibrate them. So we have the opportunity to use a lot of data, and regarding that, I think Lucas is a good source for getting that. And now we have another opportunity that maybe it will begin, but the low monitoring soil. could be this opportunity to fill the gap and the lack of information that we have in some pedoclimatic zones. So basically, the steps for me, it's at the very beginning, the harmonization of the practices, then the harmonization of these certifications or not certifications, the methodologies regarding the soil sampling and what is the timing to do and the time span to do, and then maybe, as we always said, and we always know, the models are just an approach. But if we have enough data for calibrating these models, the models can reduce the uncertainty to get the best scenarios that we can provide, no?
Hello, Matteo Jucker, Urban Data Labs. I provide data pipeline for MRV, custom data pipeline. And getting practical in the calibration of this model, I wonder if you have any insight, or you can, let's say, give us an insight on, let's say, what is the minimal region that we have to consider to calibrate a certain model? Because we all know that, you know, different ecosystems work differently and different model will perform differently on ecosystem. And personally, ROT-C is great, but my alarm is that it was made in the UK for UK soils. How does that adapt to Italy or semi-arid areas? And how much data from which region should I get to calibrate this model to make it work efficiently? Can you give us any practical insight on that?
Yes, even if ROT-C was created and developed in the United Kingdom, there is a lot of scientific literature that there are calibrated for the dryland regions. One of the main important outcomes for that is the modification of Farina et al. In 2013 that she developed the calibration for Mediterranean regions. So it's just to modify the certain inputs, but basically is to modifying that the model is that the turnover of the soil organic carbon, it stops at the very high temperatures during the summer in the summer. So there are a lot of scientific evidence. Maybe we need to harmonize all these definitions.
Okay. The last question. Okay, so last question, then we finish, and we can reconvene if you want in the afternoon, because we have the same session, but more as a panelist discussion. So please come again if you like it.
As more comment. We should also keep in mind modeling is fine, but if we have to communicate with the farmers and to give feedback about the carbon sequestration, that obviously should have taken place, but it's not taken place when you look at the farm. And then the sampling dates are very important to consider. So it can be that you sample 3 weeks later and a large part of the sequestered carbon is already lost. So when communicating modeling results, it's important to keep in mind how to communicate it to the farmers and to the practitioners.
Thank you very much. I think it's time to conclude. Thank you very much. It was a full room. I much appreciate this. This means that's a lot of appetite for this subject, and the appetite will be even more. I promise this in the afternoon, because in the afternoon we'll have some hot discussion. We don't repeat the same setting. We'll have different speakers, but a lot of discussion and hot discussion based on questions that we have developed. So please follow. Thank you very much. And thank you to all of the speakers. Thank you. Good afternoon, everybody. Thank you for coming back after the very successful morning session that was fully booked, and I hope that this will be also booked at a certain point. We are again in the second part of the session relevant to data. However, in a little bit different format. It will not be, let's say, presentations and questions. It will be a panel discussion. We have prepared a program with questions. So we'll have five very interesting panelists, and I hope that you can make the best questions in order to get the best outputs from this session. Having said that, I'm inviting the panelists to the floor, and I'm passing the floor to my colleague Emanuela, who will drive the discussion through the questions. Thank you.
Okay, thank you a lot. This morning, we talk about data and different approaches, different MV to quantify emission and removal. And we see really some examples, some presentation. We talked about data harmonization. We talked about benchmark and the baseline and how to build the benchmarks organic carbon data. But of course, the main question is, are all these data consistent? Are we able, for the given practices in a given territory, quantify the same amount of unit, or is still very dependent on the methodology we apply, on the MRV system we apply, and how we can somewhat improve the consistency across the different methods, or we need to accept that is it impossible, or we can do something, and or we can simply account for the uncertainty of the methodology, and which will be discounted to them to the credits, to the units. So we would like to open the discussion on this thing, and we have 5 fantastic panelists, and I would like to give the floor now to the panelists, so in order they can present a bit who they are and their activity, and then we will guide the discussion through some slides and some questions. So please, Tony.
So, hi. And I always forget how loud my voice is when I start talking to the microphone. So anyway, so my name is Tony Viskari. I'm currently at the Joint Research Center, actually working in Emmanuel's project. And I would say my background in general is when we have data and when we have data, how the different ways we can use that to inform our models and our projections with those models. And I have been working with the soil questions for close to 10 years now.
Hello, everyone. My name is Marina Allegrezza. I'm a PhD researcher, and mainly my activities regards evaluation of management practices by using modeling and field measurement in order to develop strategies for mitigation of greenhouse gases fluxes, soil organic carbon losses. And yes, this is mainly my background.
Good afternoon, everybody. My name is Liisa Kulmala. I come from Finnish Meteorological Institute. There we have developed a monitoring system, especially for carbon sequestration in agriculture. Many people ask maybe that why Met Institute is interested about soil carbon sequestration, but we are interested, of course, the climatic impact, but in order to understand the climatic impact, we need to understand how the nature works and what are the processes and pools in the ecosystem, and that's why we ended up in this field. Here I also represent the project MAVIC. In the MAVIC we have 7 teams around EU countries developing these operational processing chains or scalable quantification platforms, or whatever you want to call them. So those are not only models for carbon sequestration, but those are like automatized platforms where we combine models with different data streams, remote sensing, soil carbon, of course, and farm data.
Thanks, Lisa. Before I start, there is 9 of you standing in the background. Well, the 2 ladies sat down. I'm happy that you did that. And there's 9 chairs in front of us, next upon us. So welcome. We don't bite. Okay, with that, I'm Dr. Anastasia Volkova. I was born in Ukraine. I lived there until I went to uni and did my 2 masters, 1 in Kiev, 1 in Warsaw. I did my doctorate, all in remote sensing. I did it in Sydney, where I started Regrow. And regrow, some of you might know. If you don't, that's wonderful because I get to tell you all about it. We are one of the largest agriculture MRV platforms that is highly scalable, automated, and combines remote sensing, process modeling, and of course, data from the farm. Excited for the conversation today and how we're going to unpack the notion of consistency.
Yeah, thank you. What a pleasure. It's a bit loud. Is it better like this? Okay. Yeah, thank you. My name is David Kolitzos. I'm the head of the climate department at GeoVille, and I will play a bit of a different role, like compared to Regrow, who does the end-to-end planning with farming data. We're doing the spatial job. We have been doing Earth observation, land monitoring for nearly 30 years now. So we bring in, or I will bring in quite some perspective from other markets, from other sectors where we have implemented continuous data products, continental, global scale products. Remember in the earlier session, we have seen VLCC products, HL from the European Environmental Agency. These are core products that we have been developing. And there are quite a few lessons learned that I think we can bring into this discussion on continuity. What changes in time series in 5 years might be easy. In 25 years, you have different sensors who have new problems that you need to account for. So here, my position would be to bring in exactly this expertise. How to bring this together, what can help from a policy level as well, because everything we've been doing was compliant driven, either from the CAP area monitoring system, so national scale monitoring, or from greenhouse gas national inventories. This is where our core is, where we have experience in large validated data sets. And now to bring this to individual fields, I mean, this is the scale challenge that we have to address. Again, I will not have details on models that we are using for specific details, but I hope I can contribute to that part of the discussion.
Thank you a lot. So we start with the first topic. Okay, so also the audience, of course, is encouraged to intervene and pose questions to the panelists. And the first question is why consistent quantification is difficult. So is the science is not at the level? Is the process that's too variable that there's nothing we can do? Or is the data that are not somewhat harmonized? We want your opinion. Yeah.
I think that the main issue is that we are trying to simplify maybe too much some processes that are really, really complex. They have high spatial variability. I'm talking about, of course, carbon quantification and also greenhouse gases emission. We don't know which is the layer of the quantification in nitrous oxide. And I don't know, maybe if you're using process-based model like me, of course, you have the problem to account the real change between 1 year to another in the carbon quantification. And yeah, I think that it's too complex. There is still complexity. And how do you manage maybe these problems?
Okay, well, since I heard that Tony is going to disagree with whatever I say, I'm just going to go next because I'm Ukrainian. I'm not afraid of controversy. Well, now it's in the public domain. You don't know what Regrow does with data? We like pay farmers for it and then we make a big map out of it. Okay, so consistency. Why are we gathered here together? So if you're not working in the private space, you might not be aware, but basically a food company can run a scope 3 project with farmers, with their suppliers, right? And so if you imagine every company that has greenhouse gas goals right now run those projects, how do they do the quantification? So a lot of those, 40% of the top agri-food and beverage companies does it with Regrow, and so I can tell you how they do it. But of course, there are other methods. So if we think about the world that CRCF imagines, that everyone has compliant credits or other impact that's captured, the asset is captured, how do you ensure that you can compare things? If you on the farm somewhere in Puglia or outside of Puglia will do something and then someone does on the farm in Ukraine and someone does it on the farm in Iowa, how do you know if you are a big multinational company that all of it is comparable? So that's what I personally refer to as consistency. And I want to dispel two myths. First, consistency doesn't mean you get the same number every time. And this is what David and I probably will talk about it a lot, because the tools get better, the models get better, the more calibration data we get, the better the model actually is able to perform. So your uncertainty shrinks and your numbers shift. So that's hopefully where we're going with more and more data. But how do you then address, if the numbers are not the same, how do you know it is still consistent? What maintains consistency in the space of carbon farming right now is standards like Vera and CAR and Sustain Cert, where they say, here's what you need to do. Here's the rules of accounting. Please go and quantify uncertainty. Process models can do that. Now, when you account for uncertainty, take this confidence interval, 30% or 33% CAR and Vera, or maybe a different one if you're following a different project. So this is what consistency really looks like. And when a company is talking to an MRV developer like Regrow, they're asking, how do you know your model is working? And we show them a calibration validation report where we took our process model, have tested it against a lot of the on-field trials. This is not like magical data. This is a collaboration with a lot of research institutions, actual longitudinal soil carbon and nitrogen methane emission trials. You collect all that data, you run big data model with some AI on it, and you get a calibration, you write a report, you show it to the regulator checks it, gets an auditor checks it, and then you get a stamp of approval. Those are consistent methodologies. So from my standpoint, what we would like to see is people following a consistent methodology. It doesn't mean you need to certify every project that you're working on, but working with providers that provide the methodology that's certified is a path to that consistency. And then lastly, and I'll hand over to whoever wants to talk next, you of course need systems and a lot of digital systems to make sure that your data processes are consistent. It's extremely expensive, I get to tell you. Like it's not just a bunch of spreadsheets. When you do it like Regrow, we monitor 52% of the world's arable land, 1.8 billion acres. It's more than half of the world arable land, field by field. It's so much data. Then trillion data points. Then you get it updated every year, multiple times a year. Then you update your model. Then you update your uncertainty model. There's a lot that you need to keep in check and make sure you can trace the data. You can restate the calculation. If someone goes and audits a project that you did last year, you need to be able to show the data again. So I'm telling you all of this not to bore you with technical details, but to actually show you, and you can come and have a look at the software. It's, you know, it's not only beautiful, it's actually useful. That all of this exists. This is what we get to build on. And the science is constantly evolving. All the aspects are constantly evolving. But this is where we're at. We're not doing carbon farming in spreadsheets. We have traceable, auditable data that's compliant at scale.
I get to do my favorite thing ever and disagree, but no, actually, to make this a little bit more of an interactive, or momentarily interactive session, how many here feels that if someone came to you on the street and asked you, what's the difference between precision and accuracy and consistency? How many feels they could give that answer? Okay, well, we have one. Yeah, so, because they actually have, when we go into the methodology, they have very defined meanings. I'm now, because I always worry that I get precision and accuracy mixed up, so now I'm worried I'm going to say the wrong one, and there's someone say, some Emmanuel is going to be actually really hard here. But so, when we do a prediction or a projection, the terminology matters. The idea is that if we ran it for a number of sites, let's say we just do it, the precision is essentially on average, how well do we get it? So you can think of it if you have, you're throwing darts. The idea is that are you getting the dart around the circle, like the bullseye region? That's precision. How well are you throwing the dart in the right direction? Accuracy is like, well, how, when you're throwing that dart, that represents the noise in the system, because you're never gonna get it. Like, you're never gonna get consistently the same result. You're never gonna get, like, we constantly get it right. So the accuracy, just like unless, okay, well, there are world-class dart players. If there's one of you here, that's great. But you're gonna kind of, no matter how well you throw it towards the bullseye, you're gonna get it, like it's gonna go into the other values. So the accuracy basically represents how close you on average get to the bullseye. So yeah, God damn it, I knew I was gonna get it right. Thank you for the correction. I knew the moment because that I was gonna get them the other way around. Okay, but and then consistency is that, and this is actually where I think, because there are a couple of ways to think about consistency. There's like what was I just getting here, but then it's also that once we have the system, how well can we go into different places and run it there? Like that, is it consistently represented in the system? So if we are, let's say we have a really good system that works in southern France, we have a really good system that works in, let's say, Sweden, and let's say, but then someone goes like, hey, I want to run it in the grasslands of China. Are we going to basically, how well is the system going to function there? And of course, because we want to generate these kinds of models that generally work in a large, because it doesn't do us really that much good if we, on a larger scale, if we create a perfect model that works in one field in central Germany or in Boolean. We want to get a model that's able to do. And this is where it gets tricky, because the thing is that we can, to say there are a lot of just, I could say a lot because you what you said before, and I will soon pass the mic because I know that you didn't just come here to hear my sweet tone and voice. But this is where it gets really tricky, because our models are flawed, and it isn't just because we don't have an idea of the potential mechanisms or systems working there. It's that we don't have the ability to accurately it's not even a question that we get more data. The question is what kind of data we get. And that prevents us from from really building models that have these kinds of complicated mechanisms in it, which results that like the complex models produce about as well a function as the simple model. And that results that we can do a simple model and we can calibrate it to a single field, and that's going to work really great on that single field. It's going to be useless outside of it. So this is then the question of like the balance, because for that farmer or like that person working for that single field, what matters is that do you get that single field? But if you don't have a method to then go to other locations with it, that's great. You just spend a lot of resources producing a perfect version for this one person who has a 50-acre yard or something like that. But
okay, thanks. Yeah, I totally agree with both of you. Maybe what I would like to add about from modeling perspective is and consistency, that there are no black boxes, and the uncertainties are handled in a traceable manner. But also that the models are scientifically coherent in that sense that, okay, you can, if I have a model that simulates carbon sequestration based on number of rabbits and sunspots and moon cycles, and you have a model that's yeah, you have like weather and farm activities or something like that, and we both get, you know, exactly the same value, but I don't think that's consistent, you know, even though my model would be accurate. Then about this data availability part also, that we all know that in EU member states that it differs from country to country. So let's say that's in Germany and Poland, there's a similar conditions, but because of the data availability, the modeling results differs. That's of course not consistent at all. And maybe regarding EU, that it would be also very important that we align with other EU-wide rules, like with the greenhouse gas inventory, and measurements follow the same practices and so on.
Yeah, maybe two statements on that. One is I always ask, do we really need more data or better data? Because we have seen data can make things worse if they're not correct, if you just do data cleaning the whole time, this doesn't help you at all. So maybe reduce where possible. The other risk I see is that we are looking for perfection. I mean, especially the first session was, if you look through the line at the end, there was so much disagreement, error bars, like one or two comments, like, oh, this is all inconsistent. I would disagree. And the question was then, do we aim for this high standard that approves and upholds everything in all detail? But the other way is maybe like, hey, when is it good enough to start? And I think we have reached this point. So it's good enough as long as you're transparent what you're doing and you're sharing with your customer who's paying, he's willing. There's a private market, makes it easier. They can agree, hey, this is enough evidence for me to think this is something valuable for my supply chain, to bring it to the board to get paid. This is where the private market is thriving. And the policy market is like, okay, we need to, because we need to be at the end credible, we need to make a very high standard, which might not be reachable. So this is the risk that we discussing too long. I'm sure the science will get there, but we need to start before this. So there's a saying on product release, if you're not a bit ashamed of your first product release, you released it too late. So there's some trust issues. So at the end, this is a trust building exercise. You want to market, so you want someone to trust what you're doing is there. So I think we are at good enough, so we can do something as long as transparent, doing this is a minimum you save. It might be more, but we're not certain on this. This might work. And then you can go the extra miles. There were regulation come in, make standards, making this available on European market with more certification bodies in place, so more and more credibility getting there. So this is what I'd like to focus that we do not get lost in getting to perfection, because then we are too late.
The audience, yeah.
Hello, so I'm an AI researcher, and one of the things I think about in this consistency about scientific methods is also about like who's the stakeholder that's looking at this problem. Like for me, I'm a science guy, so I would like to have the more accurate, more robust methods I can get. So when I started working on this problem, I started thinking about all the data I can have, but then talking to people, someone would say, hey, I need something with maybe, okay, less accuracy, but less variables. I can only get some climate data about this field. I can get everything you're trying to get. I don't care about the accuracy you're giving me. In my point of view, I want this. Someone who's like in a company would like to be having something that's more profitable. Maybe a policymaker wouldn't care about all of this as long as he can say that this works sometimes. So it depends on the stakeholder. And while everyone is like wanting some method, how can you have this consistency in all those methods proposed by everyone with his point of view and his priorities?
Sorry. You can answer also if you want. Yeah. Ah, okay, that's good. Like changing dynamic, keeping them on my toes. Anyway, I think that's a really good question. And I think it connects to a couple of things. One is like, do you chase perfection or do you chase like the idea? So talking about like the barest component of soil carbon models. So we have these models. If you look at like, there's people who still use ROTC and stuff like that. With the MEMS model, we work with is relatively simple. The OSTA model that I work with in FMI is relatively simple. And one of the reasons for that is that we constantly found the question being that what is the least amount of inputs that we can ask for that people can give? And there's actually a really good central example of this is because we know that soil carbon state is really driven by soil moisture. Like what is the soil moisture state? What is the soil moisture time series and so forth. And so if we wanted to get a really good like understanding of what's happening in soil moisture, and also nitrogen is completely dependent on soil moisture, about how nitrogen affects the system, is that then we would have the soil moisture map. But the difficulty is that if we just have a random forest, or if we just have a random farmland, or if you say like you have a random person, we can get like the climate data. Like I can easily get the precipitation data and the temperature data on it. I cannot get soil moisture. Like I cannot just go like, hey, I'm gonna go there and then we get soil moisture. And at that point, I do think that when we generate the basic tools, when we generate the tools that are most public focused, that are most like in this, the question it needs to be built around is, what is the data they will have available? What is the kind of things that they can give us to run it? Because if we, at the risk of precision, hopefully we get accuracy about right. We probably won't, but like that is how we need to build it, because we can build, if you ask me now to build a great, like the most scientifically ideal soil moisture model, soil carbon model, I could probably within a week get you a really good one. It would be useless because there's just so many data points needed to driven that you couldn't get anywhere. So that's a constant thing that we have to keep in mind in these discussions and the trade-off in these matters. Now it's your turn to disagree.
That's right, because I'm no longer in research and I can tell you how things work in private sector. So the way you solve this is in our theory of change at Regrow, and we're a B Corp, so impact for us is completely correlated with the financial impact. We believe that if you want to see change, you need to be the change you want to see in the world. And so what is actually stopping people? How can we build enough trust, to David's point, for people to invest? What is good enough? It's not a scientific question. It's not a question of precision, accuracy, or even consistency. It's a question of how many tons out of the total carbon budget will you deduct based on uncertainty? And what will that payment be to the farmer? It's as simple as that. Everything comes down to euros and hectares, if you really want to think about it. So we've built a system that was trying to optimize for people to have a range of options. So if they had a lot of data they were willing to bring, because we actually don't see as much of an issue with that. Sure, everyone says farmers don't want to give data, but actually, have you talked to them? They have so much data, they want to monetize it. And so if you provide them a path to incorporate their data into the final outcome, and they can see how it drives the benefits monetarily for them, they are very motivated to provide you with that data. And so what you get as a result is a range of options. Some companies wanted to be compliant with greenhouse gas land structure removal standard, and that's fantastic, and that's the highest standard, and they get the full uncertainty accounting, and we run the DNDC model that we've invested $60 million into after we took it out of academia. It's still available to you as a researcher, as a publicly available tool, but we commercially are driving the modules, developing the pieces, and making sure it's evolving, because that's what's needed. It's needed for the farmer, unlike like raw sea, where it's left to its own devices, it can't handle deep tillage. That is one of the two biggest tools of regenerative agriculture. If you can't figure out how to reduce tillage, what are you doing carbon farming on? And nitrogen is a molecular problem. So for example, what is the way that molecules are behaving? What's the environment? Do you have more of these or more of those? And that's how your nitrogen fluxes are defined. Our ability to actually eat up the nitrogen and be productive as a plant. So without the model that can handle that level of nuance, you're limited to pretty high-level devices, which still have value in the market, I want to emphasize, because there's a need for systems where there's very little data, and they need to be incentivized for the transition, and you're able to provide different tools for them, like may it be IPCC equations or a cool farm tool or whatever it is. So I strongly, as you can see, stand on the soapbox of what actually gets the transition done is what we should be doing. And the way to get to that point is to unlock the capital. Capital on the demand side needs to trust enough, on the supply side needs to get enough. And as someone who runs one of the largest MRV companies, I will tell you, we are at 5% of the cost of the project. So anyone who will continue to speak at this conference about how MRV is very expensive, please come talk to me. 5%. This is what we were aiming for when we started. 5 years later, we're at that. So if you have a real project, this is, and I do mean scale, this is the numbers you will get. So at 5% to 10% MRV, everything runs. You can unlock the capital. You have your quantified uncertainty, can monetize it by paying farmers. So I think we need more investment because rigor doesn't cover everything. We don't know what to do with trees, for example. So there are pieces, of course, where I'm describing row crop and livestock sector. It's not everything. So there's more research that needs to be done.
Thank you for raising this point. It's very good. I just wanted to advertise something that we're doing in Mavic project currently. So we're studying the cost accuracy of different approaches and different data streams. So many of the stakeholders want it to be cheap and lightweighted. Scientists want it to be, and of course policymakers also, accurate and doing a good job. So we are testing like what are the cost of different data streams and what type of uncertainty they cause, like for example, the initial state, that is, something very complicated. So if we do it very lightweighted or, very complicated weighted, how much that's cost and how that ends up in the uncertainty and accuracy. Weather drivers, of course, the models have their uncertainties in their parameters and structures, and then the management. The management is also something very uncertain. So if we are, whether we are dependent on the, management from the farmer, which is complicated to get, or whether we can derive that from statistics or remote sensing or somewhere else, which is cheaper.
Thanks, Emanuele. To the first question, why scientifically robust methods often fail to produce consistent and reportable outcomes? Well, I would say it's because the tools that are used are not meant to be used this way. Scientific models have not been developed for an operational MRV context, meaning that most of the time, the modeling choices that are done, choices of models, are not adequate to what is needed. You will not screw a drive with a hammer. And that's currently what most companies are trying to do. So it's about doing the right choice in terms of modeling approach. It's about finding solutions to reduce uncertainties, like assimilating remote sensing data in a model reduces the need for activity data. I don't know any company that actually considers uncertainty on the activity data when they are doing the modeling and propagating that till the carbon stock changes. So if they were doing that, I think there would be some surprises. And one of the reasons why there is never, it never fits with the in-situ observations is because take the example of the Descent model when it was applied in the US and the shaky ground paper. I mean, they are applying a model, not considering spatial variability in biomass and input, carbon input to the soil, and they're trying to match that with measure and remeasure. It cannot match. It will never match, because if they fail to account for those things, they cannot have a good match. And another thing, we have to debunk a lot of things. We were talking about tillage. Tillage has no effect on carbon stock in temperate climates, and some models do account for that. But if they do, then, I mean, it fails to reproduce reality. It will only match. Why? Because you're measuring 0 to 30 centimeters. And yes, in this layer, you will see an effect of no-till because you're concentrating carbon on the surface. The reality is that below, you're losing the same amount of carbon. So once again, it's trying to debunk some ideas, because there's a community that's been promoting conservation tillage that has developed modeling approaches based on some false assumptions, and now we are irritating from, we have this heritage, and we have to debunk those things. So choosing the right model or the right approach, trying to reduce uncertainties with some smart approaches, definitely not using scientific tools and trying to apply them in a context for which they have not been developed, developing dedicated approach for the MRV in operational context, and debunking a certain of misleading beliefs, because otherwise we will never manage to fit with in situ measurements.
My question back to the panel.
This 5% MRV cost, does it include a repeated soil sampling and measurement?
Short answer is yes at scale. Because you have 5 to 10% at different scales. So at every scale, it would include the sampling close.
What scale are you talking about? Just to get an idea.
Well, not 1,000 hectares, right? You need to have larger. So you should model only at scale, right? Everything else you just should measure. Yeah, thank you for that question. It's great.
Any other intervention from the audience? Yeah. Oh, yeah.
Hi, Fernando from Terra Madre. Just give my perspective. I'm also from science and then moved to a project developer company or a small company. And yeah, I hear you say MRV is 5% of your cost, but then you also said that you put 60 million in developing your soil model. So I think that's shows that the investment you need to start one of these projects is very large. So it's out of the question for startups or small farms that don't have the possibility somehow to work with you or similar big companies. And my other remark is when it comes to uncertainty, we're working with natural systems, and as you know, it was just said, models are not made to be, they cannot be accurate at the site level, right? So uncertainty is inherent to what we're doing. And until we can really decrease that uncertainty to the plot level, to make these uncertainty deductions as required by Vera or whatever standards, something we can work with, it's going to be years. And I'm saying this from scientific perspective, right? That science is able to reduce these uncertainties for different regions and different practices. So first, the sector needs to learn to live with uncertainty. It needs solutions that deal with uncertainty and lets the whole sector move forward despite very high uncertainty at the farm, at the plot level. Right now, the standards are asking project developers to deal with that, and it seems like you're doing it, and I'm sure you're doing honest work. But I think that's somehow a time bomb, right? If you tell developers to take care of uncertainty, there's a high risk of bias, right? And you know, most of them can do an honest job, but it's very difficult to get your accuracy good enough to avoid huge deductions on your credits. And you know, at some, you know, someday, it's going the Guardian article is going to come out because there was cheating, and this again hurts the whole industry. So I think the solution has to come from science. Science has to give the standards, even though we're not there where we want to in terms of accuracy. So not put the responsibility on the project developers. That's my opinion.
Thank you a lot. Thank you a lot for your opinion. I just wanted to do a reflection. Yeah, we move it, but there is plenty of papers where we have long-term experiments and model that perfectly goes to the points. I also publish on this. So at a certain point, it means that they work, no? That we are able really to cope with this uncertainty. Yeah.
And how data, science, and math work.
Okay, Let's move to another topic. We talk about the MRV system. So I wanted to ask you, what is it, this MRV system? No? What is the difference between applying a models, no, a process-based model or measuring, and an MRV systems? What are the components and which are the weakest part of the MRV systems? Anybody wants to start? Yeah.
Happy to talk about MRV systems and not to talk about the questions. So I'm cognizant that others have a lot to contribute, but MRV system is a fitting question to regrow. So just to gentlemen in the back, we're not a project developer. We are an MRV provider. We power project developers, and we pride ourselves on creating independent science. And 60 million was the investment that I cited into the platform overall, which includes a lot of MRV development being an actual product that steps through the stages of enrollment, measurement, monitoring, reporting, verification, and audit associated with it. Each of the pieces of the platform are separate. So the MRV system is different from the model, because if we just think about the model, or if you think MRV is equivalent to the soil sampling, I would like to expand your horizons today, because like gentlemen mentioned, there's a measure-remeasure approach, and it's a great approach that is perfectly fitting for a lot of projects, especially if you're using a local soil sampling partner. They can deliver it for you cost effectively. But then the problem with it, and I'm not saying that I have a horse in the race. Ultimately, I want to live on this planet. I want to have children one day who will have a livable planet. That's ultimately what matters to me. And so whether we get there by soil sampling or by modeling or by shaking hands and kissing babies, I really don't care. Let's just get there. So what I found is that it's very hard to soil sample your way into finance allocation. So the way the regrow started and evolved from a model to a full system is by providing estimates that Tony spoke about when we do kind of predictions, when we look at the historical data and we say, we think from this project you can expect this volume of credits and co-benefits as outcomes, then you can actually engage financial institutions and the procurement at food companies to come and actually back a project. This doesn't mean that a project developer will deliver that exact outcome, because there's a lot in the middle. Like Lisa was saying, you know, the weather changes so much. We might think about something right now, sitting in March, by planning a project, the farmer will start planting. We don't know what's going to happen in winter. And it can freeze and it can thaw, and we can have way higher nitrous oxide emissions, dental emissions than we planned. And we just have to be transparent about it. So MRV system is effectively a process manager tool for, call it carbon farming, call it regenerative transition. That's the biggest difference with just a model. Model is a tool. It can be any calculator, and as long as it represents what the market wants to pay. And to a previous point that David made, which I thought was a brilliant point, if we're directionally correct on moving towards healing the climate rather than destroying it, we're good. Ultimately, that's what everybody's trying to do. If you source from a supply chain, then you know it's at risk. Knowing that you're funding practices that farmers want to do because they see it's working for their neighbors, we're trying to fund the transition, and it's directionally more than correct.
Yeah, thank you. I'd like to add, I mean, there are other sectors where MOV processes are in place. So carbon farming is new, but there are other sectors, if it's Common Agriculture Policy Monitoring, if it's LULUCF, it's in place since 20 years, so it's nothing new. We have produced continental scale soil sealing maps for 20 years now. And the biggest change is when you go from 20 meters to 10-meter resolution, you create, by statistics, a lot of noise. So we are discussing for month what these changes are. They are not real, they're just in the data, because of better resolution, you better see what you are. This shouldn't deflect us from actually we have a better product now. But sometimes customers say like, oh, we like this consistency, but for the cost of actually having a worse product. This is also an input to the point before. And of course, I'm an advocate for Earth observation data because it's objective at scale. So all the local inputs reduce as much as possible on irrigation practices, on management practices. There's a lot you can see from all the various Earth observation missions. So take this out of the local equation. This is many companies are doing, some more, some less, so there's potential, yes, and there's uncertainty, but don't underestimate understanding of uncertainty, and at least in big companies, they know this. I mean, if you're talking a big agro multinational company, at the end they have a supply chain, which is normally part of the financial department. At the end, they know the financial risk of my supply chain in X years is 20% or something. So we also have a company in the potato industry. They know pretty much what to expect. They know 20% of our fields are not sustainable in the next 20 years. So we need to find new sources. So don't expect that they don't know how to work with uncertainty. They know. They know quite well. They have statistics, mathematicians in this level. But at the end, it's a euro or dollar mark that makes it count. So the return of investment is very clear and an easy driver, and it goes far beyond carbon. Just instead supply chain risks or in incentives to insurance, loan management. So it goes further, quality management. So we're covering the small part of it, but when you have this ear observation part of the MOV process in place, you have so many co-benefits. And I don't talk biodiversity, this is another thing, or ecosystem values. You have co-benefits in the daily operations. Customer not saying a highly at-risk crop to a picky customers. You can lose your customer if you send a high-risk crop to them. So that's a very real use kind of scenario, which is a co-benefit of just using Earth observation data as part of the process. So then the return of investment calculation becomes even stronger. So that's an input, goes beyond this, but I think it's worth mentioning.
Thank you. So to the person, thanks, Terramar representative. I really appreciate it when you said the scientists need to give the standards, but as a researcher myself, I understand that I can't be objective there, but I'm of course tempted to agree with that. But what we have noticed in Mavic and also in More project, which just started, that the MRV systems, they need to be widely accepted. They need to be accepted by the farmers and all the stakeholders, all the key players there, and we need to really invest to get that. For example, in Finland, the farmers, they are not super motivated to fill yet another blanket, or you know, they don't see the benefits and what there is, but if we collaborate with them and try to make them also understand that this is the system and this is how it works, and then they might be also more positive for sharing the data that is needed. There was there some kind of a bottleneck, but this farm data, this activity data, that is crucial, and currently, well, I guess it varies from state member country to another, but for example, in Finland, there are a lot of these farm management information systems, and so we should somehow couple with all of them in order to get the data, but also the farmers realize that it's really really precious, or you know, everybody's wanting them, so they are hesitating to share that, and also a little bit maybe afraid that if they share it, it will reveal something that will be against them and harm them in the end. So that's why they don't want to share that if it's not mandatory or motivated.
To give a perspective, like I was thinking about the last two questions here, and of course these are the questions which answer so much better that makes that kind of at least clear. And and this is of course from now my own model developer and working perspective, but I think that one, not necessarily the biggest, because there's like the management and everything like that, but there is a certain amount of trust when you hand the data over in the results. And I don't mean trust in the sense that, oh, you leak it somewhere, but like that, hey, I give this data and they're going to run these models based on their best understanding, and it's going to give a result, and the result is the best we can get. And that's like, of course, that makes sense, because let's say you go to, like, let's say you're the consumer and you go and buy a car, and the car salesman is like, hey, I think this car runs fine. And then you get in the car and it breaks when you drive it out. And then it's like, well, I thought it worked well. And to give an example, but at the same time, models are constantly developing. We're constantly improving our understanding of the systems, and it can actually cause relatively drastic changes. So like, because you use LULUCF as an example, there's actually been in LULUCF, I could use the Finnish example, but there's been, when they do the recalculations, there's been massive shifts in the carbon balances, like in these systems, because they calculate it in a different way, or like that they made an adjustment to it in a different way. And in Finland, we have this system where they, for the Finnish forest, they did a revision where they calculated that the forest had switched from a sink to a source. And now they had to say like, no, it actually is a sink, because they did these calculations again, like they changed these things. And all of this is done with the best of intentions. No one was going there like, now we're going to do mistakes now and everything like that. But at the same time, when you, let's say you're a person, like let's say you own a farm, let's say you're in this system, and then like every 3 years you suddenly come like, hey, by the way, remember when we said that you were a sink? Like I was wrong, and like that. And it's this thing that like, I think that trust is fragile. Like, how do you convey not just uncertainty, but the kind of idea that, hey, as we develop and as we get these systems, the better understanding of this, these results might change, and how do you manage to maintain the trust through that process? But also, who is accountable in that situation? Because let's say now it happens that, let's say there's a farmland, like someone owns a farm in this system, and the MRV system comes there, and they did like, hey, we managed to sequestrate this much carbon based on our understanding of the system or methods. And then they get some kind of financial contribution from that. And then 5 years later, it's like, hey, remember when we said that? We did remeasurements. Like, no, we need some of that money back now. And then it's like, okay, who is accountable at this point? Like, because this person has acted in their best faith, the people doing the modeling has done their best faith and everything like that. And I think that's the idea that like, that to me is what makes this really difficult, because it is something where our understanding, our capabilities increase, but it constantly requires us to reevaluate these things. And nobody wants that. You don't want to reevaluate your car when you just bought it instantly and everything like that. I don't know why I ended it.
Yeah.
Thank you. Hey, I'm actually a social scientist working on carbon farming, governance and science behind it. And related to this point that you just made, which may be linked to the previous conversation about the uncertainty, I was thinking that it's a bit difficult for me to follow this conversation, because actually we are talking about different types of carbon accounting regimes at the same time. And these, like, the water gets a bit muddy, because actually we're talking about the requirements of the soil carbon markets, requirements for cap payments, requirements for value chain accounting systems. And I think all these different accountability systems indeed can afford different uncertainty levels and they have different stakes. And in relation to what you just said, well, we are paying for farmers not just because that, we need to make sure that the outcomes just should be really there after 5 years, but aren't we paying them because they've been doing this like to compensate their financial, like what they did financially to make that happen, regardless the outcome in a way. So it's a bit different than, for instance, what if there's a substitution, if we are substituting removals or emissions for removals, then we are giving emitting rights to other actors. Then the stakes are different. If we are not really giving emission rights in exchange of removals, stakes are then maybe lower. Then there's indeed more effort, we can afford uncertainty in an easier manner. So in that sense, I feel like it's these things, when we can afford uncertainty very much depends on the stakes. And it's a bit difficult to talk about these things all at the same time,
putting them all in the same basket. So yeah, that's why I just wanted to make this point to see if you have anything to comment on this. Thanks.
If you have been in the morning panelist session, there was 3 blocks. There was regulation, the outcome. In the middle, there was the yellow, which was the messy middle part. This is where we are. You summarized it. It can be very confusing. It has many elements, and this is why so many people are here, to make this messy part a bit less messy. So what do we need? Regulation. How do these CARB come together with LULUCF? How does it create to carbon farming? What are the actual demands, etc.? So there's no easy answer that I can give you now. But yeah, I think the regulation should exactly be part of that CRCF regulation to make sure that different data that are connected can be interused and connected, and so that there can be trust building from these parts. And at the end, they should work together. So they not fight together against each other, but actually have a benefit besides that. So, but it is messy. I completely agree.
I guess we apologize for the heartburn. It is actually messy. But Madam, you're making a really good point, and I just want to clarify something. I think where we are having the same conversation is because we're saying regulatory standard treats every company, despite the fact that some companies have a value chain in agriculture and some don't. They're held to the same reporting standard. And so as far as multinational in food is concerned versus an airline versus a tech company, their accounting should work the same way from a perspective of removals, reductions, gas split, etc., unless they take the land sector guidance, right? So I'm completely in alignment and agreement with you. Majority of the programs that luckily Regrow Science powers are in value chain programs. And that's how you can correlate my previous comments that we're moving in the right direction, because we work with food companies, with their suppliers, with their farmers. We're trying to move supply chains towards resilience. That's the mission of the company. I hear your point that uncertainty should be accounted differently if we are giving somebody else right to emit. And this is why it's a 15-year-old now argument about is it mitigation or adaptation? It's really both. I think that's what it comes down to.
Yeah, coming back to the consistency thing that we were discussing earlier. So I argue that we should calculate the carbon sequestration and uncertainties always in a similar way, regardless of what is the purpose. But I agree with you that we can accept higher uncertainties in different in some cases. What comes to this, this is a really good point, and I first of all, I say that I'm as a natural science background, I can't answer this. This is your field, but it's a very good that you pointed it out. That it's of course unfair that if farmer invests, doing the right thing, then we get weather events that something that are unavoidable, and that ruins the whole thing. Then it's not fair to me as a just a normal taxpayer, but how I see it is that there is a great will that it's actually the incentives and markets, they are based on the real carbon sequestration, what is actually monitored and what's actually happening, this sort of outcome-based results. And then it's your job to say whether it's okay or not.
Maybe we can change a little bit just to wake up and to go in more pragmatic, let's say, and more realistic topics. So what makes an MRV system more consistent? Let's speak about data sources. I mean, who is in favor of in situ data? Who is in favor of spectroscopy? Who is in favor of remote sensing? What type of data can make this system more consistent? And it's just one or another, or it's a mixture of many things. So, please. Yes.
And I can speak about this issue, like what actually makes an MRV system consistent on the research side. So I think that it's fundamental to include in the discussion the gaps of knowledge that we have in this system, in the model that you're using. And I think there is a fundamental question is, which carbon are you actually quantifying? Like the solid organic matter conceptualization has changed a lot in the past years. And now we are not considering the carbon as a single pool. We are considering it as a multi-pool system, you know? So this carbon state in the soil has different persistence, has different pathways mechanism, formation, pathways formation, has different response to management practices. So how are we distinguish this kind of carbon? This is the particular organic matter on one side, the mineral associated organic matter on the other side, and only one of these fractions is the real carbon that is stable in the soil. The other one has a faster turnover. We're talking about months, maybe 1 year, and it's pretty driven by residue incorporation, so organic matter incorporated in the soil, while the real carbon that is stabilized in the soil is mainly driven by microbial pool processes, microbial pool metabolization, assimilation. So is someone accounting for this issue? And another thing, I think it's important to highlight the nitrous oxide quantification, because it's not very clear in model simulation, in the simulation, which is the layer that we are counting. Like we are considering the 30 centimeters of the soil, and we are quantificating the carbon in that layer, okay? But the emission, like in that layer, 30 centimeter or 5 or 10, because it's not very clear in the research paper as well. It's not clear how are we modeling the gas transport across the soil, because nitrous oxide emission is mainly dependent on soil condition, water content, oxygen content, and these factors vary a lot through the soil layer. So how are we managing this thing? Are we going to improve our models in these directions? Are you thinking about this? And sorry, I'm making the questions, sorry. But like, I have a little experience in this field, 2 years, okay? So, and this is the issues that I'm having with simulation activities by simulating my experimental side, my long experimental side. So this question is for you, but also for the other people.
Okay.
Panos, to your question. Sure. I don't want to go to the previous question. I think I've already shared that we believe in investment in scientific tools and collaboration with academia to drive value. And I think the standards are pretty clear. They say you can measure or model up to 30, measure model up to 50. Some models do it to a meter, like the NDC. I think some of those things are defined. You have a meta question whether we're doing it the right way, but I would flip that question. As a taxpayer, when we go by the farms and we see a huge, there is the ability of soil to sequester carbon to decarbonize the planet and pull it out of the atmosphere. But another question is all of the co-benefits, which carbon is just a proxy for. And when you see all of the runoff of the topsoil, it's non-negotiable. Like you can really see what practices work, and this is why farmers want to implement it. So we can argue kind of scientifically a lot about it, or we can apply common sense that the farmer knows what they want to do, and if we're able to model that practice and account for it and get them the payment, we will get a more resilient food system. So sure, the modeling does play a role, and I hope that European Commission and other public funds and universities will invest. As a company, we will continue advocating for science and supporting it tool-wise. So, Panos, though, on your question, which I thought was a really good question, I think it's a mix. In situ data, sensors, remote sensing, and on-farm data all flow into the mature MRV. And I was talking to a customer earlier today, and I asked them a question, you know, what's your pursuing with this project? And it's like, well, lower cost MRV. So that's what everyone's pursuing. I think you need a lot of different types of data to get to lower cost MRV. You really need it, and it comes from public and private sources.
I would like to bring another aspect here that before we go into model details, we should agree on the definitions. Like, what is additionality? I think I have been in the field for years, and that has been discussed a lot. It's additionality is a different thing if you measure, remeasure, or if you model with a baseline, like in Finland, where all the fields are losing carbon. So, you know, just increasing the carbon stocks, that's not additionality, but is it additionality if we are able to decrease the release of carbon? Also, classifications. From Finnish point of view, peatlands are very central, and we argue, what is a peatland? Swedes think it's different than we Finns think. Of course, there's a IPCC, some kind of a definition, but in real life, there is you know, a lot of gray area whether it's a peat or not. So we should agree on this type of a basic classifications and land uses management things. What comes to this calibration and validation, that's my favorite, of course. Every team does that in a different manner. So, but within the Mavic project, we released our recommendations how to do it, and let's hope that the Commission will recommend something for everybody.
I'd add, just based on the work done by our group, is that there's also, to kind of throw the question back, or like to get the consideration back, it really ultimately depends on what a person determines is the consistency that they're looking for, because there's like a lot of variability in it. And for example, if you now ask me to like calibrate a model and say like, I want to get a relatively good idea, like the model to replicate the Europe scale relatively well, we can do that. Like we have actually done that, like right now. If you ask them like, hey, I want you to calibrate the model that it gets Europe relatively well 8 years from now, then we get into a relatively big question mark. And this is actually, to me, a central problem in this, like not a problem, a challenge in this discussion. Because when we talk about validation and when we talk about consistency and everything like that, we usually talk about now, because that's the only thing we have the data for. And that's like what we use for these kinds of system analysis and stuff like that. But to go back to the excellent point raised about like the farmers, they do a certain thing, it's cost back, they do a cost and they got stuff like that. That investment is for the future. Like that's the idea that this will benefit, like that the fields don't get run off by a flood, and the fields don't get. And at that moment, it becomes a lot more difficult and important to define at what point are we comfortable with this, because it cannot be what are we doing now, like how well are we capturing now, but like at what point can we determine, hey, this is the level of consistency, this is like that if we get like in 3-year or 4-year window, this is how well we got it. That's a non-answer, but I love giving them, so I'm happy with it.
Please.
Tobias Horsmann from the Secana. I maybe one thought on this notion before from customers asking for low-cost MRV. We also hear that question quite often. We want low-cost MRV, want low-cost MRV. But I think it's actually the wrong thinking around it, because in the end, project developers want to optimize for project economics. And MRV is not just a cost, it's also an opportunity to increase your revenue by having an MRV strategy that actually reduces uncertainty deductions. So I think we should always look at the sum of MRV cost plus uncertainty deductions, and that's what needs to be reduced. And that might sometimes mean investing more in MRV, because that additional investment in MRV actually means that the overall economics are better because of reduced uncertainty deductions. And I think that's maybe going back to this point on consistency and where flexibility is needed. I think consistency really needs to be on assuring that there's no positive bias to avoid overcrediting. Consistency needs to be done that every single estimator, every way how to calculate change needs to be properly assessing the uncertainties. And from then on, it's all flexibility. Everything should be allowed as long as it's not biased and as long as uncertainties are properly quantified. And then you can basically make an economic optimization game. And that's it. All right. Yeah. Of course, transparency is critical because otherwise no VVB would be able to assess whether integrity is guaranteed and no bias is happening and no uncertainties are overlooked.
Any further reactions from the audience? Yes, please.
So Andrea Pitalco, University of Padova. I'm from the FLAC community, so I'm a bit biased. And for me, carbon is just a net ecosystem exchange minus harvest. So to start. And I have something like 20 station years of measurements of fluxes on a crop, on a perennial crop. And to my experience, this number is in the range of 100 or 150 grams per square meter per year. And I use the very old but convincing example of the sheet of paper. So this sheet of paper is 70 grams per square meter. So at best, you will end every year with a couple of sheets of paper on every square meters of land. So these are the numbers. These are the measured numbers. These are reference numbers. So what is your hope? To find 2 sheets of paper dispersed in 1 meter of soil. It is a very little hope. So this is the difficulty of a direct assessment for soil scientists. And a second important topic is the geometry of the system. Soil moves, soil grows and shrinks. Soil has shrinked after tens of years of bloody agronomy plowing very deep, and soil is growing when you use regenerative policy in agriculture. And this is not accounted in any modeling of soil carbon budget, because when you miss 1 millimeter of soil, that means 10 cubic meter per hectare. So a huge quantity in the range of the yearly growth in carbon. So these are very basic thoughts about carbon budget of the agricultural land. And sorry, a last question is a very huge stone guest in the room, which is non-stationarity of the system. We don't have a climate anymore. So climate is moving. So everything is moving. And speaking about baselines or steady behavior of system is really, I think, unsuccessful.
Okay, so excellent 3 points to go from the backwards forwards. The first about the non-stationary climate, that's completely true. And that would go into a larger discussion about how we calculate the initial states generally, how we approximate them, and how we do that by steady state that doesn't exist, and so forth. And that's why it's actually important when we use these models and when we calibrate and when we do this, is that we try to get large scale calibrations, because then the idea is that we get the system responses to the varying climate conditions or varying systems, which then allows us that when the climate changes, then we can approximate. It's not going to be perfect, but we can get an idea that if it gets warmer, this is what's going to happen going forward. But that is a central issue, and there's a lot that could be dug into that. Even though I said backwards to go down the first one, that is a really good point, and that's why there's actually, in order for there to be benefit to the system, or like from the measurements, there's no point in making a measurement every year. There's no point in making, like you can make a measurement every year. It's not, the noise is going to be so huge that it's kind of a waste of resources. And for example, during my time at FMI, one of the things that we did was that we did actually calculate based on our model understanding how often should you actually measure in order to get the best estimate. And the best part of that we actually found was that the answer depended on our question about what time interval. So if we were interested in what the state is 40 years now from now or 60 years from now, the measurement interval should actually have been different. So, but it is a huge question then, because it then goes to, so how often should you actually go and measure? But and how much you should measure, because this goes to your second point about like the shifting in the system, because if you just go to one point, if we are like at a farm and we are like, well, we just walked into a farm, we took a soil sample, we walked out, we had this one soil sample, that's great. Even if you then had it like in a reasonable range, it doesn't do much good because there's so much noise, heterogeneity in the system and so forth. And that's why the measurements should be done. There's calculations like actually that have been done for grasslands and forest lands. Farmlands are a little bit trickier. Well, but not as tricky and as well as trickier. How many measurements you should get in order to get to a reasonable, like certain uncertainty range when it comes to the measurements. But this, the second part that kind of brings us, and this is really important when we understand when we talk about models, our models essentially work on the law of large numbers, which is that we get the average right. So if we basically look at that field, if we have a model that essentially works, because we like, if it's set up, even if it doesn't have the internal shifts, and there have been models that have tried to get soil advection and it's just a nightmare, like from a dynamical point of view. Then in that situation, what we actually are, that we're saying like, okay, but the carbon's kind of swirling within this same field. We're making an assumption, and I can soon tell you where this assumption doesn't hold, but we're making an assumption that it's kind of a random walker. So the carbon is staying in the same field, So even if when making those predictions, we get that like, oh, we get a single plot within that field incorrectly. If our model works correctly, we should get the total representation of the field in total, like about correctly. Where this fails is landed fields. So if you have a field that's on a hillside or anything like that, and this is, for example, why mountains are a nightmare, because you get rain, erosion, you get systems that shift. And in those situations, and it is something we kind of have an idea how to tackle that, but it's such a tricky thing to tackle that I haven't yet seen a model that really addresses it in a certain point. But excellent points overall.
Eric.
Quick thoughts about your questions. Having a very low carbon change in carbon stock doesn't mean you don't have the potential for increasing a lot the carbon. One example, if you have a crop rotation based on sunflower and wheat, one is losing carbon, the other one is storing carbon the next year. The balance of the two at the scale of the crop rotation is close to 0. But if you add a cover crop in between, then you will increase the carbon stock, and then it becomes detectable. So first thing. Then about cost accuracy. Well, there has been some work, Lisa mentioned it in Marvik and in Orcasa on that. We published a paper last week, the Iasustat al paper from based on the MRV cookbook from Orcasa, where we have analyzed some ways to increase both accuracy and reduce the cost of monitoring, and there are some substantial levers for that. One is by combining remote sensing, data simulation, and crop modeling coupled with the soil model. But so that was the second thing, and there are things also about soil initialization. If you choose the right model, actually you don't even need to do soil measure, in situ soil measure to initialize the model, because as you are calculating the difference between two modeling exercises, if you don't even need to have accurate estimate of the initial carbon stock. So you can save a lot of money with that. And so there are different ways like that in which you can both increase the accuracy and reduce the cost of MRV. And your third point was about? Okay, but you answered well on this one. It was a good point there. So nothing to add.
Thank you. Manuel.
Thank you, Andrea. You had a very good question, and I would say that first of all, it's important to sample by the same mass, by the equivalent soil mass. No, this guarantee that you take the same amount of soils, and you can take this dynamic, because if the soil shrink or not, you keep only the soil mass, the same mass, and so the model that are calibrated on this method should indirectly reflect a bit, this dynamic. And a second, let's say, important point is that indeed we are missing a process in our 99% of the models that we are using, which is the lateral transfer of carbon, especially when we have erosion, and erosion is a very diffuse net process, and the main effect of the erosion is that we a bit overestimate the soil respiration, because there is a process that detach carbon, and to keep the same mass balance, we tend to overestimate the respiration of the soils. It's the opposite in the depositional site, but the depositional site in average are lower, let's say, compared to the erosional site, which are, let's say, more. So that's another point that I would like to discuss now. How much complex, how much process should it be in this MRV system? So we see that a lot of the MRV systems use ROT-C, which is a very simple old models also. And do we need to increase the process, the complexity of the model, at which expenses is more difficult to calibrate the models which are more complex or not? This still, I think, something that is a debate, because someone said, okay, no, we use ROT-C because in our region it's working, it's simple, and that's it. But and then we are not going to predict carbon in 100 years. No, so no, we predict for 5 years, and then we have measurements, and we can recalibrate the models. Or do we need to to work in more complex model that take into account many processes?
Thanks. So yeah, that's a very good question. That brought to my mind, we're working with landscape DNTC, which is very complicated model with a lot of nitrogen processes and cycle described in detail. Yet we are still failing to reproduce the N2O emissions that we are observing in the field, even though we try to do our best. At the same time, my fellow colleagues from another institute, they are doing a pretty nice job just predicting the emissions with on peatlands with the water table depth. So there's just a very simple regression. So where the water table depth is determined. So that's just an example where, simplicity is sometimes better than complexity. But I guess with you were mentioning also this N2O dynamics. So those are complex phenomena. We still lack scientific understanding, even though we know the basics, but still, sometimes the emissions do not happen even though the conditions are there, and we still need some science. So it's I wouldn't go very easy there.
I'll come back to my earlier point that I think if there is value monetarily in complexity, then I think when there's a will, there is a way. Like if there's a market, there's an innovation to match it. When we first acquired DNTC and the commercial rates, it feels like the most complex model you can imagine, but it's also very elaborate. And over time, we've developed ways to feed in information from remote sensing, from the on-farm data. We did the sensitivity analysis to understand what was really important to ask the farmer about and what did not matter as much. So we can feed it a default number for the region. And over time, you can find where you want to spend your money and your resources. And any of these models will continue to need development. Like, that's something that everyone just needs to understand. I don't think you can keep it on the shelf and assume that the model out there is just self-improving. And if you want to keep investing in something, you want to see an ROI. So, of course, public dollars funnel that through universities. In the world of private market, we develop that IP so that we can actually funnel the capital towards the transition. So I definitely urge this group to think a little bit about what's the big picture. I know a lot of the time we work on something so specific, and I agree with Emanuele and Tony on all of the points that were made in terms of how the models handle complex dynamics. And most importantly, the fact that if we're getting it right at the scale we're trying to achieve it, we're doing what needs to be done. We're achieving the outcome, versus if we weren't even pondering any of these questions and we said, okay, David and I had a little bit of a pre-conversation because we shared a machine learning engineer, and perfect is the enemy of good. So I just urge everybody to do good today. If you're doing perfect, you're doing too much.
Yeah, and to add to this, one of the objectives here is to influence a bit the CRCF regulation. So let's keep this in mind. How can we make sure, and this, I'm not the one to answer this, the policy thing, to make sure that all the demand-driven sites, good enough for me to invest into it, and how can we match this with the compliance from the European bodies saying, oh, this must uphold to rigorous standards? How can we find a process? These are not going in different directions. How can we make sure that these align? How can we have maybe flexibility in there, that they use the same approaches, and some say, oh, we don't need all the details, but again, that they're not fighting each other. Like, are you voluntary or are you compliance market? But actually, no, we're covering this part, this is good, so that you can select. So this would be my urge to Commission and policy. Make sure that the demand, which is clearly there on the voluntary market, on the private market, and they're driving and financing this a lot, make sure that we don't end up with a regulation which is against this. This is my biggest wish from this conference as an outcome, that this align to take the drive innovation that is in the market on farmers, on agri-food industries, and make sure that European can become a flagship in terms of we have a regulation, because Europe is known for regulations, but let's make it worthwhile. Let's make it a good regulation. That's what I'm hoping for.
Any more points? Oh, still, Johannes.
Thank you very much. Just, I will speak from the hydrogeological modeling aspect, and I think for all of these questions, the answer for this will be another one question: what scale you want to simulate? So, because based on the scale that you will actually select at the end, will define the data source, will define the model selection, the complexity of your model, and what actually makes sense. So basically, I first we need to define what is the scale actually we want this MRV, and then follow up, okay, based on the scale, what needs to be follow up, maybe.
For the point. Okay.
Thank you. We work with land managers and livestock owners, and we try to transform their grazing practices so that it's better for the animals, better for the land, and better for the planet, all the deal. And as part of our projects, we try to monitor the soil organic content, and it's, in our experience, much harder to sample in grazing lands than it's in a field. And I may be mistaken, but most of the discussions here seems to be centered around agricultural lands instead of grazing lands. So my question is that, how does this modeling technology compare between like permanent grasslands and fields? Also, how is Earth observation methods currently compare in success between exposed soils versus permanent grass cover? Thank you.
Thank you. If somebody wants to give a point about the grasslands, Miss Tony.
So technically, there are different dynamics. So for example, if you have a grazing land, the assumption is that you also have more natural fertilizer in it. And there's also that, like, because there's it's almost a constant mowing effect, someone removing grass from there because there's being eaten and all of that. It's a tricky thing because from a model perspective, there's no difference. You just adjust the inputs. So basically, if you have the grazing, you just increase the mortality rate going into the litter fall going into the system. You should change the way that you changes the assumptions when it comes to how the soil temperature, the air temperature and precipitation drive the soil moisture and soil temperature or the nitrogen and like that. So it's actually more of a question of driver data, because you shouldn't drive them the same way that because for example, for grasslands, the common method is to use MPP as the annual driver data because the model, it dies, it goes into the soil and so forth. But if you have a grazing land, you probably shouldn't do that. But to go back to what works, if you don't have a better initial assumption, then you go with that. And you will get something that still should be relatively somewhere there. But then it's more like going step on what are these methods that then drive the model and what are the calculations and like that. So you might, for example, want to calibrate the model separately for a grazing land compared to a regular grasslands. But from the model dynamic perspective and a lot of the observation and so forth, it should be the same.
Okay, thank you very much. Thank you very much to all the colleagues. Yes, and of course, this is a discussion that can take hours, can take days. Sometimes we have done workshops in GRC, closed in a room. We and some other modelers, Marta is here from other projects, MRV4SOC, Marvic, discussing all the time, even not being able to give solutions to all these questions. And as you see, we have adopted a little bit the process of, or the idea that there is no ideal model. Nothing fits to everything. So let's use an ensemble of models in order to reduce uncertainty. So we'll go towards this direction. And in the next years, we'll see more and more developments towards this direction. Thank you again. And I hope to see you around for bilateral discussions in the poster session as well. Thank you.